Hey everybody, welcome to our third workshop of the year for DS3. And of course, as you guys know, this one's on deep learning. So here, my name is Tanveer, and then we also have Takashi here. So today
Hi.
we'll be basically kind of going over deep learning and neural network models, kind of get your feet wet with the math and code behind some of the most state-of-the-art models right now used in the industry for many cognitive tasks. So before we get started, if you guys want to also fill out this link here, basically give us any input on any workshops you want to see in the future, and also so we can kind of get an idea of who we have attending, that would be great. So we'll also post the link later in the chat. It'll be also at the end, but yeah. And then also outside of this workshop, we have plenty of other workshops coming up. So next week we have an advanced practice in pandas workshop coming up. The week after that, we have a competition right now going on with Neurotech on Kaggle. And in collaboration with them, we're going to be basically creating another workshop about modeling methods for their neurological data for that competition. So if you guys are also interested in machine learning, we're basically going to be applying machine learning to neurological data, like a whole different domain, which will be pretty interesting. And then after that, before the end of the quarter, we'll definitely also be having a transfer learning workshop and a database design and management workshop. Right now, those dates and weeks are not finalized yet, but watch out for Discord and Facebook for when that might happen. So overall today, we're kind of going to be starting with an overview of linear and logistic regression, and then basically kind of build an understanding of machine learning and optimization from that, and then hope to generalize it to neural networks and these more complex models later. And after we learn basically how these models work, we're also going to talk about how you guys can also then, tune them and train them so that way you guys get the best performance you possibly can when you guys are training these models. And then at the end, we'll also talk about how you guys can write code for these models. Yeah.
Okay, so from here I'll take over. So what is machine learning? Oh, by the way, feel free to ask any question in the chat, anytime if you see anything, because we're gonna go over some like mathematical details a little bit too. Okay, anyways, so what is machine learning? Basically, simply put, it is a field of computer science that teaches computer how to learn stuff, not we tell them what to do exactly. So basically we put in data and then they using the algorithms, machine learning models, generalize representation of the data, and then tries to they're going to be capable of predicting stuff as a function. Yeah. And next slide, please. And here's an overview of machine learning. And scikit-learn is really popular machine learning library in Python. And this is I just put it here to give you an overview of what it looks like. And then on the left top corner, you don't need to see the basic detail, small details of it, but you can see classification, regression, and clustering, dimensionality reduction. These are main things, but there are a lot of algorithms out there, and then people are constantly researching, trying to make it better, right? So there are so many of them, but these are basic overview of it. And deep learning fits into all these categories, but they're just different kinds of machine learning models, and we'll cover some of that later.
Yeah, and then one more thing I also want to add is that classification, clustering, dimensionality reduction, regression, these are the problems that machine learning models want to solve basically, right? So the classification and regression are supervised machine learning tasks. And then clustering and dimensionality reduction are what we call unsupervised machine learning tasks. So in this workshop, we're only going to be covering supervised machine learning, which is these two.
Right. So yeah, as Tanveer said, we're going to do supervised learning, which basically means we have data and input data and also labels for these, or so the difference between supervised and unsupervised is that in supervised learning we have a goal to try to model. So like for regression, we try to like target model numerical values. For classification, we try to model categories, right? And so for supervised learning, whatever the task is, you always have like end goal of like what input should correspond to as an output. On the other hand, for unsupervised learning task, you don't necessarily have like end goal for those because you're not given labels. It might sound complicated for now, or you might already know these things. Like, let me know if you have any questions. But basically, that's the overview of supervised learning. And here you can see we're going to cover regression, binary classification, and multi-class classification. And regression is basically, as I said, it predicts continuous numerical values. And classification, these two types, binary, multi-class, we just try to predict which category a given data fits in. Yeah. All right, so next, so here, this is most of you, I'm gonna assume you have seen this kind of graph. So this is scatter plot and then linear fit, right? And then this is a basic machine learning model, most simplest one. And yeah, so here, okay, so here's an equation for that. So y hat is called is a notation for predictor or estimate, right? People in math, like, it's usually referred to as maximum likelihood estimate. And then so this is not the actual y hat is not the real value. It's just an estimate, and then each point on the red line corresponds to the y hat with given x1, and w1 is weight vector, and x1 is input vector, and w0 is bias. So for here, 5, you can see y-intercept is 5, and then that corresponds to w0, and then w1 here for this two-dimensional example, w1 is just a slope of this line. And what it just shows here is basically it fits the best given this scatter plot. And we're going to cover how we train this kind of model, but it's just what it looks. Okay, so here is the terminologies. So we're going to use, in order to understand machine learning models, we need to have like set of rules to understand it, right? So these are like basic notation that we're going to use. Y is going to be target value or that we want to predict, and notice that y doesn't have hat here because it's just its actual value that we y refers to the actual values, and then y hat on the other hand refers to the estimate, maximum likelihood estimate. And so that's just notational things. So when you see y hat, it's just a prediction, and the other one is actual value. W1, as I said, it's a weight. W1 is bias. X1 is input data, so known as feature. And W1, W0, these are the sort of parameters by weight bias. These are the things that we train models for. And so this is a vectorized form, right? So actually we just saw two-dimensional case, but we could imagine like as many dimensions as possible for this linear regression. And so you can see this, there is a generalized form for this linear regression, which says y hat is equal to wn times xn plus wn minus 1 times xn minus 1, blah, blah, blah. And what it shows here is you can really visualize it, right? Because it's n dimensionals. We can visualize more than 3 dimensionals, but basically you have all these weights for different dimensions and input values variable for different dimensions, and then you just magically combine them, multiply, add them together, and then you predict them. You make a prediction. That's what it does. And in the vectorized form, you can write it as a matrix multiplication, and input vector is going to be a matrix, and then weight it's going to be also a matrix because it's easier to compute. Is there any, do you guys have any questions so far, or if not, I'll just keep going on. I see that some of you have joined late, so I don't know if I, let me know if you have any questions.
Yeah, so I also like to add a couple things, right, as well. So the reason why we like using vectorization a lot in machine learning, it's like a pretty big thing if you guys want to go into machine learning later and want to code your own models, is that, you know, obviously we could loop through every single input feature, right? And then multiply each weight and add it all up together using a for loop, right? But as you guys learn in your like DSC classes, right, for loops technically run in O of n time, linear time, meaning you have to visit every single input feature, right? But the nice thing about why machine learning has gotten so popular is because of GPUs. And GPUs, graphics processing units, basically are like really, really good at multiplying matrices or doing like this sort of vector math. So when we run the sort of, when we use vectorized basically calculations, like they're significantly faster running on like modern hardware, which is why like we like to use this sort of stuff.
Yes, it's a good point.
Should we move on then?
We use a little vectorized form, and often like models are written in like summation of like each variable, right? In like research papers, but you actually have to vectorize it to like run it. So you often have to like understand what's going on and try to like convert it to vectors, and that's a really important skill to have. Right. Can we go next slide? So okay, so that's just notations. So we'll go into like more interesting stuff soon, and we have to cover this really important concept of loss function. So loss function basically tells you what's like, it tells you the difference between the predicted values and the actual values. So if there's any discrepancy, like the value of loss function is going to be big. If the prediction is really close to the actual values, the value of loss function is really small, and it's often called it's sometimes called as objective. Okay, you guys might be hearing noise because my my neighbor is like doing some construction, so sorry about that. Anyways, yeah, sorry. What was I saying? So yeah, it's sometimes called an objective function or loss functions, and people use both terms. But that's the main idea of it. And then here we have root mean squared error, which is really common, mean squared error, sum squared error. And so as you can see on the right side, we have this equation for RMSE, or root mean squared error. And this is actually not just machine learning stuff. Like you see this like in many places, like obviously math and sometimes biology and like all this science stuff. And what it does is basically it if you remember, y hat means estimate, right? So you subtract you find the difference between the predicted value y hat minus the actual output label, actual value y, and I is I notice the which I data we're looking at. So like if you're looking at the first data, then it's y1, and then if you're looking at second data, y2, and so forth. And then we have n data, right? N data points, and then we compare all this predicted value and actual value for like corresponding like 1 to n, and then you take a square of it, because you don't want to well, there's mathematical reasons for it, but we're not going to go deep in that. I can't remember top of my head, but that's what we're going to use. And then we divide by n to normalize it, and then take a square root of it, because we squared beforehand. And yeah, so we're going to use this. Basically, this, as I said, this captures how far your model is from the actual data. And it's really important because we're trying to our our goal is to create a model that can predict the actual values, right? And what it means in terms of loss function is minimizing the loss function. We're trying to minimize the discrepancy between the actual values and the predicted values as small as possible. And there are a lot of methods to go about this, but basically all you have to do is that, and this idea of minimizing loss function carries on to deep learning as well, because it's just another form of machine learning model. And yeah, okay.
And one other thing also I want to note is like we obviously are talking about this like not too in depth as much, but like you guys will also, if you guys haven't taken DSC40A, like loss functions are a huge topic in that class. So you guys will definitely learn more about that if you haven't already in your data science coursework. Definitely not the last time you'll see it.
All right. So now we're going to talk about gradient descent. Gradient descent is a form of optimization, and it's used a lot because it allows you to it allows you to like optimize your model, like minimize loss function, even if the loss function is actually not convex. And we're not going to go to in depth on the math, but basically what it does is so imagine a ball, right? Like 3D ball, and loss function looks like a ball, right? And then there are like up and down, but there is like a minimum point, and we're trying to reach to the minimum point because we want to minimize the loss function. Height corresponds to the value of the loss function, and then the sphere, like surface, well, it could be like many dimensions, but I'm just saying 2-dimension for now, but it could be many dimensions. But basically sphere surface is the input dimension, right? So you're gonna have a lot of parameters. It's hard, maybe it's hard to visualize, but that's the idea of it. And then we're trying to go as low as possible on this like curve. And gradient descent is that you take a derivative, like slope of the plot at every point, and because slope is like tangent, and then it looks at the bottom, right? And so if you use that, idea is that you can technically go to the bottom. That's the idea of it. And then you can see the visualization here. So the red point is your current status of the model, and then as you iterate through gradient descent method, you try to go down in the and y here of course is a loss function, and then so by going down the hill, you're trying to minimize this difference between predicted value and actual value, and that's what it's doing. And on the left side, you see the math here. Well, its idea is that wi is the ith wave vector, and wave vector is just the parameters that you want to multiply to the input, and then every time you iterate, you update with minus alpha times the gradient of the loss function with respect to the weight. It sounds complicated, but basically the idea is the same as earlier. Like it's just in terms of math, it looks complicated, right? And the alpha is a learning rate, and it tells you how far you want to go on left or right direction each time, and then you can change the values of alpha to make it go like move it faster or slower. Like it's usually less than 1. It's 0.1, 0.01, or like something, and you can choose any values between 1 and 0, basically.
Yeah, we'll also talk about that a lot later. Like in the hyperparameter tuning section, we'll talk about like how we go about choosing learning rate. But like I also want to add, right? Like the reason why we have these two separate equations, even though they kind of look like the same thing, is this is kind of like the update rule we use for like a singular weight with respect to like the ith input feature, right? Like this is how we update the weight for with respect to the ith input feature. And this is the vectorized equation where we try to basically update all the weights with just one single computation, which is why like it's much faster to use the second one, where instead of having to loop through every single weight and update it one at a time. So that's like the difference between these two equations, where this is taking the partial derivative and this is taking the gradient, which is a vector of partial derivatives for all of the weights. Next slide too.
You always vectorize. Yes. Right. So now we're going to talk about really basic classification model, which is called logistic regression. It says logistic regression sounds like a regression, which regression usually models numerical values, but here we actually use it for classification. So we have given data of like x1, x2, let's say, and then like label like true or false or something like that, and we're trying to train our model to be able to predict which category given data would. And then logistic regression, on top there is this function, it's called sigmoid function, and it's 1/1 plus e to the minus t, and you can see the graph below. So basically, so whatever the so d is the input here, right? And then if you put 0 into z, for example, you can compute it 1/1 plus e to the 0, which is e to the 0 is 1, so 1/2, so it's 0.5, and then so you're gonna see the curve like this, right? If you plot the thing, and basically if you have positive, if the input is positive, then it will return positive values between 0.5 and 1, and if it's negative, if it returns 0.5, value returns values between 0 and 0.5. And basically we're going to use this as a probability of how likely the given data is for given classification. So for example, if the input value is 6, it's close to 1, so we're going to predict the category and given input to be like really likely to be a positive class. And on the other hand, if the input value is -6, it's really close to like 0, so it's gonna be classified as negative class and stuff like that. And so you can look at the math here. Basically, so D is actually linear combination. If you take a linear algebra class, you're probably familiar with the term linear combination. But linear combination basically means like you have these weight vectors and input vector, and then you multiply the corresponding ones and then add them together, and that's gonna be the Z, and then you're gonna put that in there. And this is the same thing as a regression we used earlier, and at the bottom you can see the loss function of this logistic regression. L refers to logistic regression, and then so inside, ignore the summation for now. So inside summation we have yi, which is a label, times log of y hat, and that's the this is cross entropy loss function. Cross entropy, we're also not gonna go in depth with the cross entropy, but basically cross entropy is another loss function. Well, because we're trying to model classification, right? Like if the given class is positive or negative, we're not using some mean squared error, because it's just really two different separate tasks, right? For regression we can use mean squared error. For classification we can use we mostly use cross entropy loss, and cross entropy is just a term for like classification objective function, and the idea behind it is you try to if you know math, then you use like Bernoulli distribution or a more optimized, if it's a best model for multinomial distribution, if it's if the number of classes is more than 2 and stuff like that. But well, just remember the cross entropy is for classification. That should be enough. Yeah. Okay. Well, okay.
Do you want to go back or do you want to keep going?
I can talk about this too. It's similar things. So basically, Softmax regression is an extension of logistic regression, and on the top right, you can see sigma function here. It looks more complicated, but it's basically the same thing. But because we have logistic regression is for two classification. Like, do you have a cancer or you don't have a cancer? Are you male or female? Like stuff like that. Those kind of problems can be solved with logistic regression, but for for classification with more than 2 classes, for example, like what are you wearing, like t-shirt, shirt, like hoodie, and stuff like that. Like you get what I mean. And these regression classification tasks are called Softmax regression, and then we have this sigma function. And well, actually, math is the equations are pretty similar. It's just you just have like more classes to classify. That's why it looks more, but it's similar things. So you also have to minimize the cross entropy loss function, and the idea is pretty much the same as logistic regression. Right.
All right. So from here, like we obviously kind of just built like a pretty good like I guess kind of background, and I think from here now on, like this presentation will be like a lot less math and more like kind of generalizing what we just learned, but to more complex models. And we won't be introducing as much math because the math only gets more complex. But like honestly, to build your own models, you don't need to understand it too much, but it is definitely really, really helpful. But we'll kind of start before we get into like deep learning models is like kind of like how deep learning became as popular it is today. Like obviously you guys know that deep learning is like used for everything between like analyzing news to self-driving cars these days, right? But like it wasn't always like that. Like deep learning was discovered and rediscovered many times by many different researchers in the 60s, right? And it was even like recurrent neural networks and basic things like that were discovered here at UCSD, like back then. But back then, like deep learning was definitely way more controversial at the time. Like people didn't really see a really big use for it back then because there were many things holding it back in the fact that there were many problems with it when it was trying to learn with certain types of data. There was also many problems with the processing power holding it back, right? So sometimes the models would be like too complex for what you're trying to solve, right? So some of the more traditional models like decision trees or just basic regression, like were better and outperforming deep learning at the time. So people like, this was like a huge debate for like many decades that why even use deep learning when we have all these other simpler models that outperform it on most tasks. And that's why like the era between like the 60s and up until like 1985 was basically considered like the first AI winter. At least that's what we call it in CSE 151B. But this was like basically deep learning started becoming more popular when Geoffrey Hinton, a researcher at University of Toronto, along with some of his other grad students, basically published a paper that applied the deep learning gradient descent algorithm to a neural network architecture. And before that, neural network models already like were defined and existed, right? But they didn't really have like such an easy way of optimizing the parameters in that model before they applied deep learning to it. So this paper was kind of revolutionary and made people kind of realize that, you know, like deep learning isn't as complex as we thought it was before. And then researcher Jan LeCun in 1989 then was the first one to basically create a demonstration of deep learning for handwritten digit recognition using a basic neural network. And this was basically the first real industrial use of a neural network for any task in industry. And then since then, like we've obviously had many advancements in research where people have been developing many more state-of-the-art models and solving many of the problems that came with deep learning, as well as like companies such as NVIDIA or AMD or Intel coming out with new, faster hardware that enables people to do deep learning on a much larger scale and with much more complex data and much more complex models. So like some of the roadblocks that kind of hinder deep learning don't exist today. Like back then, people would have like hundreds of lines of code of vector math, implementing machine learning models, right? But as you'll see later in our code demonstration, you guys can now literally create deep learning models in like 6 lines of code. It's crazy how much easier it's become since then. So why would we ever want to even study deep learning, right? Like obviously back in the 60s, right? People thought that other basic models are much easier to use, right? But basically deep learning models, right, are ones that use neural network architectures. And the places in which the neural network models outperform like your other traditional machine learning models is where data is like really, really high dimensional. So when we're dealing with things such as like images, vocabulary that is like really, really high dimensional, LiDAR data, like these sorts of, this sort of data is like in thousands of dimensions, right? And you can't just expect to use linear regression and be able to do that sort of stuff very, very well. So deep learning models kind of revolutionized like how computers would be able to do these type of cognitive tasks, such as like image recognition, language modeling, self-driving, path planning, all that sort of stuff. However, one thing to note, guys, is that deep learning is not like perfect on every type of machine learning problem. Like if you guys are doing like things in your machine learning classes where you guys are just doing basic regression with like a pandas table, right? That data is not very, very high dimensional. And deep learning will actually get outperformed by many other simple models like decision trees or even regression models at the time. So sometimes deep learning is always not what you want for supervised learning models, sorry, for supervised learning tasks, but it's really, really good for these sorts of cognitive tasks. So before we kind of get into neural networks, we also want to talk about like the basic building block of a neural network, which is called a neuron, right? And the neuron is kind of like, obviously, like this is definitely an oversimplification of how an actual human neuron works, where you're transmitting things along the dendrites, and then when like a neuron hits like an activation threshold, right, it will then transmit to the next neuron in your brain, and that's typically how like your brain works. But so it's kind of based on that idea, but it's definitely an oversimplification where each neuron basically has weights to the input before it, and then weights every input and takes a weighted sum of it, adds a bias term, applies an activation function, and then has an output for that specific neuron, right? And what we just learned about linear regression, logistic regression, softmax regression are actually just like those regression models are just actually just neurons. So neural networks basically then are connecting these neurons together to create like much more complex architectures. So this neuron right here, right, would basically take the weighted sum of these 3 inputs, right? This neuron would also take the weighted sum of these 3 inputs. And then they would be, what we would call these layers are fully connected layers, where every single neuron has a connection to each other, as you can see. Like there's no neuron that isn't connected to each other in some way. So that's what we call either densely connected layers or fully connected layers, as you'll probably hear in terminology there. So we'll talk about a little bit about forward propagation. So what forward propagation is basically the actual math and the equations behind how your model takes an input and then comes up with an output, right? So we just saw here how we have an input layer, right, that transmits inputs to one like neural network layer. This neural network layer computes computes outputs and sends them to the next layer. This layer computes outputs, sends them to the next layer, and then we finally have an output, right? So that is the idea of forward propagation, where we want to take input data and come up with a prediction. So we, of course, we talked a little bit about this earlier. We're going to use vectorization for that, where we have a weight matrix for layer L right here. We multiply it by the input from the previous layer, add a bias term to it, or a bias vector in this case, right? So if we have like 4 neurons, right? The bias vector is going to have 4 values in it, right? Where we add 4 values to the output of this. And then after we compute this, right, we want to then apply an activation function. And then we'll, in a little bit, we'll also talk about why activation functions are kind of important. But that is basically how like a specific layer in the network will then calculate the output and then send it to the next one, and so on and so forth. And also, if you guys have any questions, like please feel free to like in between pauses, like unmute your mics or even just send them in chat. We kind of want to make this as interactive as possible as well. So this is kind of another little more complex diagram, right? So I wanted to basically talk a little bit about this weight matrix right here, right? So right here, if we have this hidden layer, so another thing that I'll talk about, some of the terminology. So the first layer in our neural network, we typically refer to as our input layer. Any layers that don't actually compute the final output from our model are called hidden layers, right? And then the last layer in our network is called an output layer, right? So if you want to find like the dimensions of your weight matrices, right? If a hidden layer has 5 units and the layer before it has 4 units, then our weight matrix is going to be 4 by 5 values, right? And that means this layer technically has 20 parameters that we're trying to train. So on and so forth. If we have 7 neurons here, 5 neurons in the layer before it, this layer technically has 35 trainable parameters that we're trying to learn, right? And this keeps continuing. So this is kind of like the general rule of thumb. So you guys can kind of have an idea of like what your network's actually learning, basically. And then next, we're going to talk about like activation functions and why you guys want to use them, right? So obviously, you guys saw that we, for a neural network layer, we would take the weighted sum of inputs, right? And then apply an activation function to them afterwards. And why do we do this? The reason why is, right, let's say, for example, we didn't have an activation function and we just computed the weighted sum of inputs and then just pass it on to the next layer, right? If we had like a really, really complex neural network with like thousands of neurons, right? Your network is, in that case, no better than just a basic linear regression model. Because without an activation function, your network can only solve linear problems. And if you start, and I'll also give a demo of this later so you guys can actually see this later. But if you guys trying to solve problems with data that is not linearly separable, if that's a term for it, then your model is going to like suffer horribly. So basically, you want to use non-linear activation functions so that way the network can learn how to solve more complex problems, more non-linear problems. And then these are some of like the most common activation functions. We obviously talked about sigmoid already and softmax already, but we've also have ReLU and TANH. And right now, ReLU is like the most commonly used activation function in the industry. So this is like the 4 activation functions we were just talking about. So this is TANH. TANH basically outputs a value between -1 and 1. It used to be used a lot in the 90s until ReLU was discovered. So TANH has some problems with it during training where sometimes weights can become a little too large or too small. So typically ReLU is like preferred for your hidden layers. And obviously we learned about sigmoid, right? People used to use sigmoid in hidden layers as well, but it's not exactly an optimal activation function to use, except for the output layer when you're doing binary classification. Because for binary classification, this activation function is perfect because it outputs a value between 0 and 1, which corresponds to a probability of it belonging to a certain class in binary classification. Yeah, so I also wanted to give you guys a little demo. Let me also copy this link so you guys can also play with it on your own. I put that in chat really quickly. So right here, this is, can you guys also see this right now? Like just type in chat if you guys, I don't know if you guys can see this right now.
Yep, I can see that.
Oh, dope. Okay. So basically, I'm going to go through a little demo here about how a model's trained, right? So right now we have a basic neural network with 2 hidden layers, 4 neurons, 2 neurons, right? And right now, if we want to solve this classification problem where we want to separate the blue dots from the orange dots, right? we will, oh wait, also I'm going to use no activation function, just a linear, so just a linear function, right? No activation function right now. We can solve that just fine because the data can be split down the middle and it's what we call linearly separable. If we want to solve a problem such as this circular problem, we're going to separate the blue dots from the orange dots, right? With no activation function, our model doesn't know what to do. And the loss is just stuck like that, right? So to solve this, if we want to, we can then use a nonlinear activation function in ReLU, and our model is able to learn to separate these blue dots from the orange dots in a nonlinear fashion, right? And if you guys want to also see this demo on like other data right here. So this data, data represents a problem called XOR. If you guys are familiar with binary logic gates, this is the exclusive OR problem. So if we use what's it called, a model with no activation function, our model doesn't know how to separate the blue dots from the orange dots at all because it's not a linearly separable problem. But if we apply ReLU or any other nonlinear activation function, our model then figures out how to separate the blue dots from orange dots right here. So yeah, we'll like also return back to this demo later when we're talking about learning rate. But do you guys have any other questions about this before we move on? Feel free to unmute your mics or just type in chat.
I have a question about the difference between ReLU and a linear regression. Like on the graph, I feel like they are similar. Just ReLU can accept values that are negative.
Yeah. So there are some mathematical reasons for that, right? I think that's something that I was also confused about at one time, right? But because we're computing it with this max 0x, right? By definition, this function isn't linear, even though it looks kind of linear, right, compared to this, right?
Mm-hmm.
We kind of just get rid of negative values. And that is literally applying a nonlinearity to our function. I could be a little more in depth mathematically about it, but I don't think that's my place. I don't think I'm like, I don't have the knowledge to basically give you a better answer, but like it is still applying a nonlinearity, which is why I can solve these like nonlinear problems, if that makes sense.
Okay. Thanks.
Yeah, no problem. Yeah, do you guys have any other questions? Otherwise I can move on. But also like feel free to mess around with this link. It's like really, really useful. You guys can like add more hidden layers, mess around with activation functions, learning rate. Super, super cool little website to mess around with this stuff. All right, so we'll continue and talk about backwards propagation. So we kind of just covered forward propagation, right? Which is the process of taking an input to the model and then computing an output, right? So that's basically computing from left to right through your model. Then backwards propagation is when you actually compute, once you've actually computed the loss with respect to like a batch of input data, right? Like how far off your prediction was from like the actual target value you want to predict, right? We can then basically calculate the gradients with respect like of the loss function with respect to the weights, right? And then try to change the weights in a direction that would minimize the loss function, right? And the way that it does this in the way that we do this in code is we actually use the multivariable chain rule. So if you guys have taken Math 20C or 10C, like you'll learn about the multivariable chain rule, and you'll take the gradients with respect to like if you're like looking at the output layer right now, right, and you compute the loss function, you'll compute the loss function gradient with respect to the output layer, right? And then you can break that down then to take the gradient with respect to the output layer's output to layer 2's weights, and then so on and so forth, and kind of propagate it backwards the network. So the math behind this is like pretty complex, and I don't really want to overwhelm you guys with the math behind it, but especially because if you guys use deep learning libraries, which we'll talk about at the end, right? Deep learning libraries already implement backpropagation for you automatically. All you actually have to do is define forward propagation calculations, and then deep learning frameworks will automatically take the gradients and different derivatives for you. But if you guys are curious about learning about backpropagation, take a look at this link here. I can even post it in chat so that way you guys can see for yourself. Anyway, I will then move on. Also, feel free to keep asking any questions. So now we'll talk about hyperparameters, right? So we've kind of defined what a neural network is, what it does, how it works. Now we'll kind of talk about how you guys want to actually optimize these models and actually like fine tune them, right? And so we learned about what parameters are, right? Parameters in your model are the things that you want to learn, the weights and the biases, the things you want to basically change to minimize loss, right? Hyperparameters are more like fixed values that aren't learned, but you adjust yourself to basically adjust the training process of the model. And unfortunately, there aren't very, very good ways to like, find the most perfect and most optimal hyperparameter values, right? So in most cases, the best thing to do is like have a good intuition for the effect of different hyperparameters on your model's training, right? And what effects they can have. And then kind of do guess and check until you find what you think is optimal. And as you train more models and build more machine learning models, like you guys will develop pretty good intuitions on how you can tweak one value and then what you see from the model basically. So, but if you guys also want like a more scientific or experimental way of like finding hyperparameters, you guys can basically use grid search, randomized grid search, or cross validation. And what grid search is basically you define like, let's say if we were trying to optimize learning rate, right? We define like 3 learning rates you want to try, 0.1, 0.001, 0.0001, right? And what grid search would do, right, is it would try every single 3 learning rate and then print out like the loss and the accuracy of your model afterwards, right? And then you can, based on that, pick which learning rate you want to use based on which one like performed best, right? So grid search is kind of like a trial and error type thing where you just try every single hyperparameter and then pick whatever performs best. So yeah, and then obviously some of the like what I mean by hyperparameters is guys can adjust things such as learning rate, the regularization lambda constant, the amount of hidden layers you use, and the amount of neurons you use in each of those hidden layers. And of course, it's not limited to just this. We're not going to talk about every single hyperparameter you can possibly adjust, but know that there are plenty of other things you can adjust about your models. So here we'll talk about learning rate. So Takashi touched on this a little earlier, where this was like the update equation we saw when he was explaining the when he was basically explaining gradient descent, right? So this alpha term right here is the learning rate, right? And what this alpha term basically controls is how drastically we want to adjust our weights, right? So if our learning rate is like, for example, too small, right? Our model is going to take small steps towards the minimum amount of loss, right? And if our learning rate is actually just too small, right, it might just get stuck and not able to move towards the minimum, right? Like, let me see if I can draw right here. So like, if your loss is right here, right, and you start going down, your model can get stuck, like maybe even right here if the learning is too small, unable to move because the weight updates are just too small, right? And then if our learning rate's too high, right, what might happen is we might just jump around way too much back and forth, not able to actually converge to the minimum point we want to, right? So to get the most optimal learning rate, you really want to find like a little happy medium between too high and too low. So that way you're converging decently fast and towards the minimum, basically. And as you guys train more models, you guys get a better intuition of this. But I can also give a quick little demo. I gotta also figure out how to erase this stuff from the slides because, okay, there we go. So next I'll also really quickly go back to the demo. So I can kind of give you guys a little, demo of like a learning rate that's too high and a learning that's too low. So if let's give this model a learning rate of 3, like really, really high, right? As you guys can see right now, the loss is jumping like back and forth like crazy, right? And then it's never able to actually converge because it's just jumping back and forth, just like this diagram. If we then select this loss that's too small, let's restart the training process, right? It's very, very slowly reducing, right? And now it's kind of stuck where it's not able to get any lower than it is right now, right? It's still getting lower, but it's just way too slow, right? So if you want the most optimal learning rate, you want to find something that's kind of in the happy middle, right? And from here, we can see the loss is like decreasing pretty well, and it's able to solve the problem better now, right? So that's why you can't have like a learning rate, like you can't have just one learning rate that kind of solves every problem magically. You kind of have to fine tune it a little bit and mess around with it. But do you guys have any questions about that? If not, I'll just keep moving along then. Okay, so I'm going to also talk a little bit about a problem that many of you guys will encounter when you're training your model, especially for the first time, right? Which is overfitting. This is a pretty important problem in data science that you guys will encounter in your classes too. 40A, I believe, talks about it. DS3 also talks about it. And every single other machine learning class you'll ever take for the rest of your life, we'll talk about it. Even I've been asked questions about overfitting in like job interviews for machine learning roles and data science roles. So it's a really, really important problem that you guys need to learn how to solve. And the idea is, if you, for example, are given a data set, right? And you train all your, you train your model on that entire data set, right? And you get like 100% training accuracy or 100%, like zero loss, right? On that training set, right? And then you give your model like new data, right? And it starts performing horribly and you don't know why, right? Like, why is my model not able to predict on other data, even though I'm getting like 100% accuracy? And the reason is, like, the analogy I like to use of why this happens is like, if you're like studying for a test, right? Like you're studying for like a math exam the next day, and someone posts like the answer key to the tomorrow's exam, like really like early, right? And you're like thinking, oh, you're chilling, right? I'm gonna get 100% on this next exam because I know the answer, right? But then you go tomorrow and you get a different form of the exam and you completely flunk it because you didn't actually spend time studying it. You only studied the answer key, right? Same exact idea. If a model trains on training data, it already kind of knows what the answer and what the prediction is for that data. So it's going to perform like perfectly on the training data, but then not know how to generalize its intuitions to like other unseen data. So that's like the general idea of it. We also, of course, have a little Pikachu meme to like kind of explain that. But some of the solutions we kind of use to solve this problem is we also want to use a testing data set that is separate from the trained data set. So the idea of it is where if you have like a data set, right, you maybe take like 30% of those values and then you separate it as a test set, right? So that way, whenever you finish training, right, you can then immediately see how your model scores on the test set, and that way you have a kind of an idea of how your model is doing and how it generalizes to other data, right? And it's also kind of important that, so like, you also want to make sure that like your testing data set or whatever you use to figure out how good your model is also not drawn for the same distribution your training data. Like, you don't want the testing data to be too similar to training data, because then otherwise like real world data is not going to do well with the model. And then there's obviously other solutions to it, which is regularization, which we'll talk about next. And also you can decrease model complexity. So if you have like too many like layers to your model or too many neurons, right, your model is like really, really complex and will learn the most specific weights it possibly can on that data. And it won't be able to generalize as well. So sometimes like less is more in the world of machine learning. Like sometimes it's best to have like the lesser complex models to do better, if that makes sense. So right here, regularization is basically a mathematical calculation that we use to try to make our model less complex. And the idea is, to a loss function, we will add these like L1 and L2 terms, or we'll typically just add one, never both, to our loss function, because then our loss function is not just computing the difference in between our predicted value and the target value, but it's also taking into account how large our weights are, right? And the model doesn't want to have very, very large weights, because larger weights typically mean it's relying on one specific feature a little too much, or the model's like too complex. So this basically helps penalize like large changes in the weights from gradient descent, so that way the model can generalize a little better. And this lambda term right here is also another hyperparameter we want to adjust sometimes. Because like a higher lambda, right, would penalize like larger weights more. So you can increase it basically if you're having the overfitting problem. But obviously increasing it too much would sometimes make your model weights not able to change as well. So the training process can be slowed or unable to move, similar learning rate. And then, yeah. And then another thing that's like, you don't have to exactly tune this, but it's something we should also talk about, which is optimizers. So optimizers are basically mathematical computations that we can add to like the training process to reduce the noise when we're trying to reduce loss. So I'll kind of like draw a little picture here to kind of visualize what I mean by that. So if we have like a 2D drawing of a 3D surface, right? So this is technically a 3D surface I'm drawing in 2D, where right here is the minimum point that we want to get to. This is the smallest amount of loss that we want to get to, right? So our model is starting at a really, really high loss right here, and we're taking steps towards the most minimum loss, right? But as you can see, we're kind of going in like other directions, noisy directions, and that's due to like the statistical noise that we get from each batch of training data, right? So the idea is optimizers want to use a moving average to basically negate some of that noise, so that way we move like more directly towards the minimum. So by that, if we have like a model that's training out here, right, with an optimizer, instead of taking like big steps to the left or right, it'll go more directly there. If that makes sense. It'll take much cleaner, much less noisy steps towards the loss, right? If that makes sense. And if you guys have any questions, just let me know about this. But some of the most commonly used optimizers are atom, momentum, RMS prop. They all have differences between each other, right? But most people simply just use atom. Like it's typically considered like the best optimizer right now in the industry. And there have been some improvements to them, but but not really that much. So typically just use atom if you want to get a good model. But let me know if you have any other questions about that. Let me just clear all these drawings. All right, so now we're going to basically go on to talk about some deep learning libraries and less about like the math behind machine learning. So the core idea, so basically machine learning, the deep learning libraries were not exactly built with the purpose of deep learning, right? Like they were not built with like the ability to be able to just train models like that immediately out of the box. The core feature of a deep learning framework is the feature of automatic differentiation. And what that means is the deep learning library you're using will have like matrix multiplication or like other functions you can use, right? Other calculations you can use. And when you define these calculations, right, the framework's backend is then going to basically construct what you call a computation graph while performing those calculations, right? So I can draw you guys a quick computation graph so you guys get an idea of this, right? So if you had the function 2 multiplied by 3, 3 plus 5, right? Let's say you were computing this with your deep learning library, right? It constructs a computation graph where you have 2 times 3, right? So you combine these using the multiplication function, right? And then you have 5, and then you add 5 and the output of 2 times 3 together to then get your final output, which is 11, if that makes sense, right? So if we were defining basically this computation, right? This is kind of what the computation graph would look like in our model's backend. And what this is really, really useful for is that when we have our final output from the computation graph, we can then, there's a lot of code already written in the library's backgrounds where it can then take the derivative of this final output with respect to the values in the graph, right? And this is used through like a lot of data structures and optimization that's like way beyond the scope of anything I know or anything you guys need to know. But just know that's like really, really cool that you guys can literally compute anything, and then these libraries know how to take the derivatives automatically really, really well. So the idea is for machine learning, right, is you can define a set of steps to compute a model's predictions and then compute the loss at the end, and then the library will automatically know how to take the derivatives and gradients with respect to that loss function. So that's like why it's super useful for machine learning. But of course, keep asking me any questions if you guys have any. So we're going to talk also about like the two most used machine learning libraries. So the first one obviously is TensorFlow. I'm pretty sure most of you guys have probably heard of it. It's an open source machine learning library that was created by Google, backed by Google, and people all in the community, in the open source community, are constantly uploading to it and also collaborating with Google engineers on this. And the reputation of TensorFlow is basically that it's the library that's used definitely the most in industry and for production, right? Its competitor, PyTorch, which we'll talk about next, is typically used more for research purposes, but TensorFlow is typically used more for like actual industrial use, which is the main difference, right? And because it has the big backing of Google, right? Google has developed so many great ways that you guys can actually then deploy your machine learning models to use on your phone, like for phone apps, how you guys can maybe deploy them to websites using like TensorFlow JavaScript or other different tools, right? And within TensorFlow, right? So TensorFlow, when it first came out, right? TensorFlow 1.0, it was pretty popular when it first came out, but a lot of people in the machine learning community really did not like it because the syntax of TensorFlow literally didn't even look like Python. Like people would call TensorFlow not even like it was not very Pythonic. That was what people called it, right? So it was very, very unpopular in the machine learning community at the time, and that's why people really, really liked PyTorch more back then. But in TensorFlow 2.0, basically, right, they made a lot of adjustments in the syntax to make it more Pythonic. And they adopted another machine learning library created by Francis Chollet called Keras, which basically is a high-level API that uses TensorFlow as a backend to create your models. And I'll also show a code demo at the end where you can basically create like a really simple, like a pretty complex neural network in almost like 4 lines of code. So Keras is like really, really useful and really beginner friendly for you guys to create your models in. And it's now a part of TensorFlow, which is why TensorFlow 2.0 is like pretty popular right now. So, and then obviously there's also PyTorch. So PyTorch is also very, very commonly used. It's an open source deep learning framework created by Facebook. So you kind of have these tech giants, Google and Facebook, that are kind of competing for the love of all the machine learning engineers and data scientists out there in the world. And the reputation of PyTorch is that people see PyTorch as a library that's way more easy to customize and way more Pythonic. So that's why it's used a lot more in research, because when people are implementing these like new state-of-the-art fancy models from scratch, they really need that customizability, which is why they like PyTorch more. And PyTorch is a rapidly evolving library, right? But as of right now, it's not as easy to deploy as TensorFlow, but like it is getting there. Like people are creating great tools for you guys to be able to deploy your models to websites and phones and other sorts of things like that. But it's not at the same level as TensorFlow for being able to deploy these models for those types of cases. And then, so like unlike Keras, which is now a part of TensorFlow, right? PyTorch also has a high-level API called FastAI that was created by Jeremy Howard, another deep learning engineer from Carnegie Mellon. So FastAI is not actually a part of PyTorch, but it's a really, really beginner-friendly way of creating models using PyTorch as a backend. And it's like pretty beginner-friendly. I know a lot of people who've like taken Jeremy Howard's like machine learning classes, and that's how they got into machine learning. So it's really, really easy like that. So you guys can also check that out if PyTorch is a little too like demanding for you. But regardless, between these two machine learning frameworks, like you guys can't make a wrong decision. Like picking either of these up is relatively straightforward, and you can always like if you learn one, you can pretty much always learn the other if you really need to. So last but not least, before we kind of finish up here the night, I kind of also give you guys like a quick demo of what Keras looks like and some Keras code. So right here, I'm going to basically run through this in just like 7-cell notebook of how you guys can train models to classify handwritten digit images, right? So we'll run some import statements here. We're going to import NumPy. I also am using this MNIST library to basically more easily read in the training and testing data. And we're also implementing all these different things from TensorFlow.keras. So we'll talk about that more later. So we'll load in the data right here. And while that's loading, I'll also run this next line right here. Shouldn't take too much longer, hopefully. There you go. So as you can see right here, our training data set has 60,000 examples and has 784 dimensions, right? A 28 by 28 image. And then our labels for the training data set are 60,000, like there's 60,000 labels for the 60,000 images. All right, and these are what the images look like. After that down here, we're going to talk about like, this is how you basically create a model in Keras, right? So you create a model through what you call the sequential API in Keras, where you give Keras a list of layers, and that's how it defines the architecture. So we talked about before how these layers are typically called either dense layers or fully connected layers, right? So when we use a dense layer as we import from here, we're actually using just a basic neural network layer, right? With 256 neurons and using a ReLU activation function. And then another dense layer with 128 neurons and ReLU activation function. And finally, last but not least, this is the output layer using Softmax, because this is a multi-class classification problem where we're predicting if the digit is between 0 and 10, right? So we have 10 output nodes, one for each different class, and we're computing softmax on the last output. And then obviously right here, we also define the optimizer we want to use, which is Atom, which is typically what the best optimizer is here. And you can also in here define what you want your learning rate to be and mess around with that. And then this model.compile function will then initialize your model, set it all up in the back end so you guys can start training. So we'll run that now. Just really quick. And then right here, this model.fit function is what you guys use to then start the training process in the given data. So you give the training data you want, specify how long you want it train it for, and then of course how many images you want to load in at a time, speed up the training process. So we'll kind of start that up. Shouldn't take too long. Like, yeah, there we go. It's going pretty fast. But as you can see, we're getting about 85% accuracy to start, and we're up to almost like 97%, which is pretty good, I think. And if we want to just plot, see how that looks, you can see our model is kind of minimizing loss during the training process, and accuracy is going up pretty well. And then if we want to see how well it does in the test set, right? Here we see that we have a 97% accuracy on the training set and then 95% on the test set. So there is a slight overfitting problem here, which we could obviously apply regularization to or make the model less complex for, but isn't too big of a deal. Like the model is still pretty good with such a very small amount of training, right? And you guys can obviously mess around. Like I do have included the code if you guys want to mess around with it, but you guys can add more layers, decrease more layers, mess around with the neurons, all that sort of stuff pretty easily, because I think Keras is pretty nice with how easy it is to like create a model. Like all this sort of stuff like 40 years ago would have taken hundreds of lines of code, but you guys can literally do it in like 4 lines of code. Yeah. So yeah, that's going to be pretty much it for the night. But I'm going to also basically this is some other resources that are pretty useful for deep learning. So where at least I personally learned all my deep learning was through Andrew Ng's Coursera classes. And if you don't know who Andrew Ng is, he's the guy who formed Google Brain and also the founder of Coursera. So his Coursera classes are really, really good, right? Even if you don't have a strong background in math, he breaks the math down pretty well. So you can always follow around, just follow along and take notes. And it's pretty easy to follow, even if your math background is not strong. And it really helps you build those fundamental skills in machine learning. And that's how exactly I learned my first year. If you guys want to also get involved in machine learning projects, I highly recommend going to Kaggle, getting yourself involved in a competition, download some data sets to mess around with and build models for. If you guys want to keep up with like what kinds of projects people are doing with machine learning, you guys can read from Tor's data science blog on Medium. And people are creating all sorts of blog posts about the interesting stuff they're doing with machine learning and deep learning there. And then Reddit's also a really good source if you guys want to keep up with what's the most state-of-the-art models of the time, right? r/machine learning, this subreddit is pretty good because people are always making posts there about like some of the more interesting research papers and models coming out of places like Facebook, Google, and other major universities, right? So if you just want to keep in touch with some of the newest advancements in the industry, like Reddit is actually a great source to be able to do that. And if you ever want to go into machine learning, right, in the future and build these custom models, it's like really, really important you learn how to read research papers and understand what the most cutting edge work is, because a lot of machine learning work in the industry is just reading like the newest research papers and then implementing all the stuff from scratch. So it's definitely a good skill to like develop on if you want to go into machine learning full time later. And then I also included like this little blog post about how you guys can go about tuning hyperparameters right here. And if you guys also want access to these slides later, we'll also be posting them at Facebook and Discord later for your guys' use. But yeah, you guys are free to go. Thank you so much for stopping by. We didn't have too much for turnout, which is disappointing. But if you guys have any questions, we can stick around for a bit.
I also want to point out that we also have neurotech competition, right?
Yep. So definitely, like, if you also want to get your feet wet with a machine learning competition, definitely check out the neurotech competition. Lets you kind of apply machine learning to like a whole new domain in neurology, which is super useful. Basically, another org on campus, Neurotech X at UCSD, they collected data using a brain-computer interface, and using the brain signals that they've collected, we try to build models that predict whether your right hand's being raised or your left hand's being raised. So it's a binary classification task. So if you're looking to get yourself involved in machine learning, definitely get involved in that competition. And there's like Amazon gift cards to go along with that too.